Hello everyone, welcome to this video. In the previous video we have seen how we can calculate or is the first operator equation solvable or not, or what is the combination of operator equation by which we can solve that particular equation. So we saw in the previous video that in order to solve the first equation, that is connected with the fourth operator equation. So here we'll talk about the solvability of third operator equation. So if you remember, what was that equation? So we have T cross F minus lambda F is equal to G. So this was our third operator equation where T cross, this is the adjoint corresponding to T, which is what is T? T is a compact linear operator defined on the normed space X, right? So now we will talk about the solvability of third operator equation, this one. So here, according to this theorem, we have if T is given to be a compact linear operator on a given normed space X and lambda not equal to 0 is also given to us, this is some complex number, right? Then they are saying equation 3 that has a solution f would be the solution to this equation for a given G, right? G is already fixed. When f would be a solution if and only if G is such that G of x is equal to 0. So that means when we input x into G, that is equal to 0. And what are all these x? They are all those members which satisfy equation number 2. And what is equation 2? That is the homogeneous counterpart for equation 1. Our equation 1 was Tx minus lambda x is equal to y, right? Where y was some given number from the normed space X or given vector, right? Lambda again was some complex number which is fixed. So they are saying if g of x is equal to 0 for every solution Tx minus lambda x is equal to 0, then third equation has solution, and conversely if third equation has solution, then for this particular g of x is equal to 0 whenever x is the solution of equation number 2. And moreover they are saying if second operator equation Tx minus lambda x is equal to 0 has only the trivial solutions, that means x is equal to 0 is the only solution, then equation 3 is solvable for any value of this functional g here. What is g and f? G and f, they are functionals which are taken from the dual space of the normed space X, right? So this is what the theorem tells us. Now let's see how we can go on and prove this theorem. So here, first of all, we assume that equation 3 has a solution f and x satisfies equation 2. So what we are required to prove here? We are required to prove that g of x is equal to 0. So to prove g of x is equal to 0, let's see how we can proceed. Now because f is given to be any solution for equation 3, that is t cross f minus lambda f is equal to g, then we are required to calculate what is g of x, and we have to show that g of x is equal to 0. So let's proceed. G of x is nothing but, now from here we can substitute the value of g, that is t cross f minus lambda f. So we have t cross f minus lambda f times x. So when you separate out the terms, you have t cross fx minus lambda f of x, and then using the operation, using the definition for adjoint operator, t cross f is nothing but f of t of x, right? So we have this term according to the definition for adjoint operator, right? And the second term over here could be written as lambda f, could be written as f of lambda x. This lambda, because it is a scalar quantity, could be taken outside or could be moved inside, because f is some linear functional and this scalar does not affect it at all. So now we can again club the terms because f is a linear functional. So we have f of t of x minus lambda x. Now we also assume that x is a solution for equation 2. So that means tx minus lambda x would give us 0 because x is the solution for this equation, and f of 0 is basically 0 because f is a linear functional. So therefore you saw that g of x is nothing but 0 in this case if we assume f is a solution for equation 3 and x is a solution for equation number 2. So this proves our first part. Now in order to prove the second part, let's see how we can proceed. Now for the second part, we assume that g of x is equal to 0 for every solution x of the equation tx minus lambda x is equal to 0. Then we have to prove that equation 3 in this case has a solution f. So we assume that x is the solution for equation 2 and g of x is equal to 0 for every solution, and we are to prove equation 3 has a solution here. So we assume x is some member of the normed space, and we here substitute y is equal to t lambda of x. Remember what is t lambda? T lambda is t minus lambda I, right? So obviously now if we apply t lambda onto some member from the normed space x, so it would obviously belong to t lambda of x because small x was some arbitrary member of this space. So y also belongs to the range space of d lambda x. Now from onto this range space we can define a functional. Let's call that by f0. So this functional is defined in such a way that f0 of y is nothing but f0. Now we are substituting the value of y here, that is t lambda of x, and what is all of this? We are defining this to be g of x. Now we have to check whether we have defined it correctly or not. So this is a correct definition here. Why? Because if we consider two different members here, t lambda x1 that is equal to t lambda x2, the value of this function g of x should be equal, right? So we assume t lambda x1 is equal to t lambda x2. So we shift whole of this thing to the left hand side. So you have t lambda x1 minus x2 that is equal to 0, right? And now we can open up the definition for t lambda. What is t lambda? It is t minus lambda I. So you have t lambda of x1 minus x2, that is t minus lambda I of x1 minus x2. So you can open up the bracket. So you have t of x1 minus x2 minus lambda times x1 minus x2, because I here is the identity operator. So when you multiply identity operator by any element, that you get that element back, right? So this thing is equal to 0. Now what does this imply? It implies that you have t of some element here minus lambda of that same element that is equal to 0. So that means this thing is nothing but the solution of equation 2. So we have x1 minus x2 as a solution of equation number 2. If that is so, what is this? According to the definition here, this is g of x1 minus x2. So you have g of x1 minus x2 is equal to 0 also. Why? Because x1 minus x2 is a solution for equation 2, and for if x is the solution here, tx minus lambda x is equal to 0, by the assumption we are assuming g of x is equal to 0. So we have g of x1 minus x2 is equal to 0. So we can open up this thing. So we have g of x1 that is equal to g of x2. So here we have proved that if we take two different inputs, we get as equal. That means if we take two different inputs here which are equal to each other, we get the two different results which are also equal to each other, right? Equal inputs provide equal outputs. So this mapping is well defined. Okay. Now this functional which we have defined just now is linear. Why? Because we have defined it in terms of t lambda and g, and both of them they are linear. So next we have to show that this functional is bounded. Why this is so? Because later on we shall be using Hahn-Banach theorem which is only defined for the bounded functionals. So here f0 is linear, that is okay. Now we have to prove f0 is bounded. For that we have a lemma whose proof we have just skipped here. So let's not go into the proof and come to the main result. The result here, it states that if t is a compact linear operator on a normed space x and lambda, which is a non-zero complex number, is given to us, then there exists a real number c which is positive real number, which is independent of y in equation 1, and such that for every y for which equation 1 has a solution, at least one of those solutions. So we are talking about this equation tx minus lambda x, that is equal to y. Now they are saying for every y here, at least one of these solutions, so at least one of those solutions x which satisfy this equation for a given y, we are calling that to be x tilde. So that solution x tilde satisfies this condition. It satisfies that norm of x tilde is less than equal to c norm of y, where what is this y? Y is t lambda of x. So using this lemma here, we will prove that f0 is bounded. So using the above lemma here, we say for every y which is a member of the range space t lambda of x, at least one of the x that satisfy, at least one of the x means at least one of the solution for equation number 1. So that satisfies this condition, that norm of x is less than equal to c, which is some positive real number, times the norm of y. And what is y? Y is t lambda of x, where here the real number c that does not depend on y. So here, from here we have marked that f0 is bounded. Now using the boundedness of f0, we can say that what is the modulus of f0y? That is equal to, by the definition, f0y is nothing but g of x, and we can now open up the modulus here using the properties of norm. It is norm of g multiplied by norm of x, and what is the norm of x? That is less than equal to c times the norm of y, right? Now we can combine this thing, c norm of g, that is c tilde. We are calling this to be c tilde. So finally we have c tilde the norm of y. So we have the modulus f0y less than equal to c tilde norm of y. So this thing is bounded. f0 is a bounded linear functional. So here we can apply the Hahn-Banach theorem, which provides the extension to the linear functional. So we can say that the functional f0 has an extension f, right? And that extension is also a bounded linear functional defined on whole of the normed space. So we can define this f of tx minus lambda x. Once we have the bounded linear functional with us, which is a linear extension of the functional f0. So f is the extension for the functional f0. So we can expand the definition for the functional f, t of x minus lambda x. So we can separate out the terms. Now you know what is t lambda, that is t minus lambda times I operator, right? So therefore we can write t minus lambda I to be t lambda of x. Now what is f? That is f0. So f0 of t lambda x is nothing but g of x, using the definition for the functional which we have defined above. So this is one part. The second part here gives us another definition for f of tx minus lambda x. So using the definition for adjoint operator, first of all, because this is a linear functional, so we can separate out the terms. We can take lambda outside, and here we can apply the definition for adjoint operator. So this term, first term here, becomes equal to t cross f of x, right? So now we can club up all the operator terms together. So this would be t cross f minus lambda f times x. So this is the second definition for f of t of x minus lambda x. So we can combine these two definitions. So from here we can clearly see that this term here is equal to this term here. So we have g of x is equal to t cross f minus lambda f times x, showing that what is this f? This f is the solution for the equation number 3. So if you see clearly, what is this? G is equal to t cross f minus lambda f, that is nothing but our third operator equation. So in this way we have proved the second part also, the converse part also. So I hope you understood this theorem well, how we can solve the and see which conditions are available for solving this third operator equation. Well, that is it for this video. Thank you for watching.